is this reaction process is really crucial for sort of drug synthesis by putting two reactions together to sort of increase the efficiency of that and also reduce waste coming off of the reaction. So let me introduce sort of the molecules that we're working with. Amines are nitrogen-containing organic molecules, or rather one type. There are several types, but nitrogen is found in about 75% of bioactive molecules in drugs. So a lot of natural compounds like caffeine, morphine, and nicotine, as well as drugs like lipitor, which is used to reduce cholesterol. So in lipitor, you can see that there's a black nitrogen and a green. The green nitrogen is found in a different sort of nitrogen-containing structural group, functional group, called an amide. And in my reactions, I'll be making both amides and amines. That's black nitrogen. Can you hear me in the back?
No.
I think better. Moving on. So in order to make amines and sort of bioactive drugs in general, we have to take multiple step syntheses. So a very common synthesis pathway involves making an amine and then making some other functional group with nitrogen by forming more bonds to that nitrogen. So oftentimes that's an amide, as you see in these groups. They both have a functional group which has nitrogen, which is bound to a carbon, double bound to an oxygen. You can see that highlighted here in purple. Now, the way these usually progress is there's an amine formation and a purification, and then you do another step to create the amide. This is a very common pathway. Make the amine and then the amide to make your functional group and keep going with drug synthesis. So another important aspect to these amines, to these functional groups, is their chirality. So these molecules have an orientation, and they're similar, but not exactly the same, sort of like your hands. They have all of the same components, but they're actually mirror images of each other. So you can't really lay them over on top of each other to get them to match up. So if you look here, this amine is actually behind the molecule, and this one's in front. They're not exactly the same. They're oriented sort of different. And this is important for drugs. One, an enantiomer, that's what the left hand would be called, can actually have different biological effects. The right hand can cause some side effects that you wouldn't want, whereas your right hand enantiomer may provide some life-saving treatment. So, in sort of the traditional organic synthesis, you actually typically make both of these at the same time, and then you have to purify one out so that you get the activity that you want. Now, this is sort of wasteful because you need to purify a ton of stuff out. You get about 50% yield, which is much lower than you would get enzymatically. This also occurs using many organic solvents and metal catalysts, which are hard to dispose of compared to water, which we use for an enzymatic reaction. So transaminases, which are enzymes that we use to do these reactions, are actually much more efficient because they both increase yields, because they only make one enantiomer. They only make, say, a left hand instead of making a left and a right. And we can also conduct these experiments in water, so milder conditions than the organic solvents, at room temperature and without the use of very sort of pollutant metal catalysts. So a typical transaminase reaction occurs in equilibrium. This means that the products and the starting materials, once the reaction reaches equilibrium, are form products and reform starting materials that are on the same rate. We need to take steps to sort of enforce the product side of the reaction, so we push the equilibrium towards the product side so that we get the product that we want. Now, there are two standard methods to go about this. You can increase the concentration of the amine donor, which is one of the starting materials, to increase the product concentration. Or alternatively, you can remove one of the products from the equilibrium to push the equilibrium towards the product side. Now, the typical less efficient than maybe if you were moving the product that you want. So our solution to this is by putting the reactions in tandem. We can remove the product that we want, by immediately reacting it in a second reaction to generate another product that we want, rather than focusing on the co-product, which we would have to purify and remove anyway. Doing it this way removes the purification step in between the amine synthesis, which we just did enzymatically, and the amide coupling, which we will do as the second reaction. So, we're removing our product, the thing that we want, in this case it's the green dot, by incorporating it in the second reaction to produce our final product, which is purple stone here, which we would use for, well, that's sort of a key step in, say, the drug synthesis. So, very important molecule, we need two reactions together to do that more efficiently than we otherwise would, because there's less purification. And we're spending more time focusing on the actual sort of molecule that we're concerned with, rather than removing co-products or like side product waste things. So there's just this second reaction, the amide coupling, which we've added on to the enzymatic reaction, would typically occur in organic solvents. And this is something that we have to sort of account for, because water isn't similar properties to organic solvents. They're much more cold. So we use micelles, which are sort of a container which creates an environment similar to an organic solvent, in which our amine, the green dot, can react with a carboxylic acid or crop protecting group and form our final product, the thing that we want. And these are really good for that. Very efficient. So, one potential issue we could have with our reaction is that since we're using an amine donor, that black box, the overall reaction, is one of the starting materials from the enzymatic reaction, that could potentially form an amide. So similar to our final product, using the starting material instead of that intermediate that we're focusing on, the green dot, there's the potential to form that black double diamond, awful sort of side product we don't want, and that would reduce our reaction efficiency. So in order to sort of test this, let's set up two different micellular reactions. So an amide coupling by itself in the micelle to test whether the starting material would form an amide, so black double diamond, or whether our reaction with intermediate product would form the amide that we want, purple stone. So I did this two different ways. So the first reaction, the setup, it's a 1:1 ratio. So one equivalent of the acetylcholine, which is the starting material, one equivalent of the reaction intermediate, which is the green dot, and one equivalent of the reacting, which is a carboxylic acid. And we reacted those and saw that if you look at this far left peak is the starting material, coupled as amide, and this is sort of one. So when I actually ran these competitive experiments, we saw that we had a much higher concentration of the product that we want compared to what we didn't want. In fact, it's actually about 87% yield. 87% of the product that we need was the amide that we wanted, as opposed to 13% was the undesired side product, which is pretty good selectivity for this reaction. For the second test of this, we set up a very similar reaction with a different reactant. This one is another very common step following the amine formation. It's not an amide coupling, but it's, again, a very common second step after that. So on this one, I actually got better efficiency had about 90%, or sorry, 95% of the product that we made was what we wanted, and only about 5% was that sort of side reaction with starting materials. So, for the enzymatic reaction, sort of the first reaction that would occur on this path, right? Set up the calibration curve to sort of determine what the concentrations of the product would be. And during that process, as Dr. Hastings already mentioned, our HPLC pump broke down and I had to fix that. So after sort of dealing with that, went in and finally had to look at my products for the reaction. And it turns out that the enzyme didn't actually form a new product. So we had to go back and figure out what sort of went wrong. So the first thing you do when something like this happens is you test the enzyme for whether or not it's working. And this is called an enzyme assay. The standard assay for our particular enzyme is actually the reverse direction of the reaction that we're doing, which is immediate time. So we did that assay. We saw if you look at the blue dots, show that that enzyme is actually working, converting our product to co-product back to the starting materials in terms of our reaction. The way we want to go is that we wanted to form a product to co-product. So I did that assay. As you can see are the triangles. And it didn't work. So this means that in spite of sort of our research into the enzyme, it didn't really do what we were expecting it to. We're looking into other enzymes. So I'll be screening those some new enzymes to find one that fulfill this easy. And while doing these assays, it sort of prompted us to look at some other sort of issues that we may have with our enzyme. Now, one of these is the enzyme could potentially break apart our final product, which would be kind of a bummer. So there's potential for the enzyme to break our final product, purple snowman, back into one of the first reactions, and sort of a mess of the intermediate product and another one of the reactants from the second reaction. Now, to determine whether this happens or not, we do a simple assay set up similar to the other one, where we just put those products, so the final product, in a container with the enzyme and see if it reacts. Now, from that assay, we actually saw that no reaction occurred. So once the enzyme conducts the first reaction and the amide coupling happens, the second reaction, which pulls our product out of the first reaction, it actually goes to product and it stays there, which is excellent for sort of the concept of the tandem reaction, because it shows that it will work as long as the enzyme's functioning and we get our concentrations to where they need to be so that everything's working together. So, the next steps in my research, I'll be screening enzymes to identify one that works well for this particular reaction. Since the first one didn't really work out, we have those already. We just need to set up the reactions. And the calibration curves are ready to go, so I can determine how much product I actually need. And then after I find an enzyme that works well for this reaction, I can finally put together the tandem reactions and see how it works. We know from some of Tom's research in Dr. Hastings' lab that we may have to play around with concentration with it to get them to where they need to be so that the reaction is working well in both the enzymatic and micellular stage. But that should be okay. We know that they don't really interfere with each other. From some other research done in Dr. Hastings' lab, and this should all work. So, do you have any questions? Any questions?
Is there a sort of mechanistic understanding of why an enzyme would work preferentially in one direction rather than the other? And that was unexpected to me also, that if I understood.
It's somewhat complicated. I mean, you should go give it a stab.
So the way enzyme active sites work is, I understand. I'm going to try this. There's sort of a fit which, so starting materials come together in the active site in one direction, right? And they fit together. And the best fit is actually the transition state. So all the starting materials are reacting in the active site of this enzyme. Their best fit is there. And then they form a product after a bond is made or something like that. And then leave the active site. That can also happen in reverse, where the product comes in and it can undergo some change so that it's the transition state. And it goes back in the other direction and reforms the starting materials. So in some enzymes like this, since the kinetics of the reaction are sort of neutral, if it's not particularly favorable in either direction, it's balanced, you can get a back reaction there.
Yeah, more or less. I mean, it depends on the thermodynamics of the system. Like the forward reaction will be favorable under some conditions, like if you swamp it with one reagent, and it'll be, the back reaction will be favorable if you swamp it with, the other reagent on the other side. The issue here was that a mean donor that works best with this particular enzyme, one, interferes with micelle formation, so we don't want to use alanine, which works best with this enzyme because it interferes with micelle formation, which is another finding that Ted made that didn't talk about. And the other thing, yeah, I think that was the main issue. So right now we're in the process of getting our hands on an enzyme that works really well with isopropylamine, which is a better amine donor that we can use in excess without screwing up the downstream reaction.
So this particular amine donor, it actually is working much better in reverse. The enzyme is.
Yeah, I
That is
mean,
your reverse assay.
presumably we could really bias it if we used you tried 20 equivalents or something. I think if we used 100 or 500 equivalents, we could probably push it. But we knew based on Ted's results that wasn't something that we wanted to touch anyway.
Right, but just that the backward reaction is the one that's working.
Yeah, I think it tends to be more favorable going in the left-hand direction because that CO double bond is conjugated to the benzene ring. But you can overcome it by swapping.
In general, when you're trying to find an enzyme that's going to catalyze a reaction to one, how much of a shot in the dark? Is there any real guidelines to step into to say you think this enzyme is likely to be one that's going to do what we want, or is it pretty much you're out on a limb trying to figure this out?
So transaminases are pretty general enzymes.
Some of them are, yeah.
They're found in basically every living thing. Everything needs them to actually react with alcohol. In biology, there's a lot of recycling. So a lot of research goes into identifying them because other people do similar research work with these this experiment. But from other published works, we can sort of get an idea of how we should react based on other researchers' findings and that sort of thing. That's actually how we identified a couple of other enzymes to try and work with the reaction. And a lot of them are expressed by companies that sell them for reactions. So they have a lot of published findings on what sorts of reactions they work with. Answer your question.
Any other questions? If not, let's thank our speaker again.